This glowing orange ring is the first direct image of a black hole, but for physicists, this dark center represents a mathematical dead end, the site of a contradiction that suggests our two most successful theories are logically incompatible. General relativity defines black holes through the lens of gravity. To Albert Einstein, they were regions where the warping of space and time becomes so extreme that matter is crushed into a point of infinite density. This classical view led to the no-hair theorem, which posits that once matter falls in, its unique details are erased. From the outside, the resulting black hole is defined only by its mass, electric charge, and spin. Every other piece of information is locked behind the event horizon. General relativity also demands that the event horizon is not a physical barrier. Following the equivalence principle, an observer falling toward the center would notice nothing unusual as they crossed the threshold. The passage into the interior would be smooth and drama-free. But these smooth, large-scale equations eventually collide with the laws of the subatomic world, quantum mechanics. Quantum mechanics rests on the principle of unitarity. It states that in any physical process, the information about the initial state of a system must be preserved. If you have the final results of an experiment, the laws of physics must allow you to mathematically reconstruct exactly how it began. In 1974, Stephen Hawking combined these two worlds. He applied quantum field theory to the curved space around a black hole, looking for how subatomic particles would behave on the edge of the void. He discovered that quantum fluctuations near the horizon produce pairs of virtual particles. One falls into the black hole, while the other escapes to infinity as thermal radiation. This process slowly drains the black hole's mass until it evaporates entirely. The problem is the radiation itself. Hawking's math showed it to be purely thermal, a random hiss that contains no information about the matter that formed the black hole. If the black hole disappears, that original information is gone. This is the information paradox. If Hawking is right, the laws of quantum mechanics are violated. If the information somehow survives, then our understanding of gravity must be incomplete. When a black hole evaporates into featureless radiation, a pure quantum state is transformed into a mixed state. This transition breaks the mathematical link between the past and the future, making the universe's history irrecoverable. To resolve this, physicists proposed black hole complementarity. They argued that information is both reflected at the horizon and passed through it. Since no single observer can see both locations at once, the contradiction is avoided. In 2012, a new analysis, the AMPS paper, showed this compromise fails. By looking at a black hole that has evaporated past its halfway point, researchers found that the quantum connections required to save the information would physically tear space apart. To satisfy quantum unitarity, a particle of late-stage Hawking radiation must be entangled with the radiation that was emitted long ago. But to satisfy the equivalence principle and keep the horizon smooth, that same particle must also be entangled with its partner falling into the black hole's interior. Quantum mechanics prohibits this. The monogamy of entanglement principle states that a particle cannot be fully entangled with two independent systems at once. To save the information, the connection across the horizon must be broken. Severing this quantum link is a violent process. It creates a massive, localized release of energy at the boundary of the black hole. This is the firewall. If it exists, any observer attempting to cross the event horizon would be instantly incinerated. The smooth, empty space predicted by Einstein would be replaced by a wall of high-energy particles. This leaves a choice between two impossibilities. Either information is destroyed, or the most basic prediction of general relativity is wrong. Some theories, like the string theory fuzzball, resolve this by suggesting black holes have no true interior or horizon at all. Instead, they are dense, solid states of vibrating strings that store and release information directly from their surface. A different breakthrough emerged in 2019. Physicists using the replica trick began calculating the entanglement entropy, a measure of how much information is shared between the radiation and the black hole. These calculations produced the Page curve, showing that as the black hole shrinks, the entropy eventually drops. This proved mathematically that information was indeed leaking back out into the universe. The math worked because of replica wormholes. geometries appearing when calculating the probability of quantum states. These aren't traversable tunnels. They are mathematical links emerging in the path integral to bridge the interiors of different black hole copies. These wormholes lead to the island formula. It shows that at late times, a region deep inside the black hole, the island, is mathematically identical to the radiation outside. The information isn't moving out, it is simply part of the same quantum system. Because the radiation already contains the interior through this holographic link, the entanglement across the horizon never needs to be broken. The information is saved, and the firewall is no longer necessary. For the first time, researchers found a way to reconcile the smooth horizons of relativity with the strict information-sharing rules of quantum mechanics. But the math suggests a trade-off. To make these theories match, we have to reconsider what space and time actually are. In these models, the area of a surface is exactly proportional to the amount of quantum entanglement between the particles on either side. This implies that geometry, the distance between 2 points, is not a fixed background, but a physical reflection of how those points are quantumly linked. While these results are currently limited to specific mathematical models, they provide the first concrete description of how gravity and quantum information interact. The black hole information paradox did more than identify a conflict in our theories. By forcing us to track information through the warping of space, it revealed that the fabric of the universe may be an emergent property of the quantum world.